Engineering teams currently spend thousands of hours tweaking static text strings, attempting to find the specific phrasing that triggers a perfect AI output. Yet, in production environments, these highly optimized prompts often fail when they encounter complex, multi-step reasoning tasks. Looking closer at these failures, the bottleneck isn't typically the wording of the question. The breakdown occurs because the model lacks the necessary information in its active working memory to complete the request. There is a significant gap between treating a language model as an oracle that requires a specific incantation and treating it as a component within a broader system architecture. Relying on static text while ignoring how data actually reaches the model is a primary reason why enterprise generative AI projects struggle to move past the pilot phase. Andrej Karpathy, a pioneer of modern deep learning, observes that while English is the new programming language, the core engineering skill has shifted. It is now about managing the context window. This approach is called context engineering. It is the discipline of building dynamic systems that deliver precise, relevant information to a model at the exact moment of inference. Prompt engineering focuses on a single static question. Context engineering builds the automated pipeline that assembles the surrounding data on the fly. If you hire a consultant, prompt engineering is like handing them a single sticky note. Context engineering provides a complete briefing packet containing the data, history, and constraints they need to perform. Moving from raw data to reliable machine reasoning requires a transition away from prompt-centric development toward engineering the context. This block represents the context window, a finite computational space defined by strict token boundaries. Mandatory zones immediately claim this space. The system prompt occupies the top section, followed by the conversation history in the middle. The remaining capacity accommodates the retrieved context, where tools live, and the generation zone to compute responses. Due to system instructions and buffer overhead, your effective budget is roughly 40 to 60% of the advertised limit. Using the context window as an unmanaged dumping ground for data quickly exhausts this usable computational memory. These limits exist because of token economics, the mathematical cost structure inherent to all modern AI architecture. Most language models utilize an attention mechanism with O(n)² complexity. This means the computational requirements grow exponentially as you add more tokens. In this model, doubling the context length does not double the cost, it quadruples it. When developers force-feed large documents into a prompt without curation, this quadratic scaling leads to massive spikes in cloud computing costs. This math directly impacts latency. High token counts force the model to work longer, causing users to wait several minutes for a single response. Because every token incurs an exponential tax, expanding the context without a management strategy is an architectural flaw. To manage these costs, Anthropic developed the ACE framework, a structural approach to context management. The first module is the generator. It produces new information, such as tool results, added to the pipeline. The reflector acts as quality control, removing redundant or inaccurate information. The curator is the final editor, compressing the filtered data to ensure it fits the strict token budget. Efficient systems utilize delta contexts to minimize computation. Instead of reprocessing everything, it computes only what changed, layering it onto a stable base. This framework transforms an unmanaged block of text into a curated, cost-efficient data stream. Even when budget is not a constraint, a model's ability to reason is limited by how it processes the information it is given. Researchers at Stanford identified the lost-in-the-middle phenomenon. It shows that a model's accuracy is directly tied to where information is physically placed within the prompt. Transformer models prioritize data at the absolute beginning and the absolute end of the context window. When critical facts or instructions are placed in the middle of a long prompt, the model's performance can drop by more than 20%. Since spatial arrangement determines accuracy, where you place your data is just as important as the data itself. Some argue that the new 1 million token context windows from Google and Anthropic make this type of engineering unnecessary. This belief is largely supported by the needle in a haystack test, where a model successfully retrieves a single fact hidden in a massive document. However, finding a single data point is a retrieval task, which is a very low bar for machine intelligence. Real-world tasks require a model to synthesize information from multiple different locations. In these scenarios, performance on massive contexts often degrades. For example, an engineering team might ask an AI to debug a 100,000-line codebase. The agent can locate a specific function, but it often fails to resolve the actual bug. The failure occurs because the model cannot synthesize how separate microservices interact if the critical dependencies are buried in the middle of that U-shaped attention curve. On a large scale, massive context windows provide an illusion of capability that can hide significant reasoning failures. Solving the problem with our coding agent requires moving past prompt engineering and applying the principles of context architecture. We can use the curator role from the ACE framework to handle the synthesis requirement. Rather than providing the entire codebase, the curator extracts only the specific logic and dependencies relevant to the microservice interaction. These extracted snippets are then programmatically placed at the very edges of the context window to maximize the model's attention. This shows that reliable, enterprise-grade AI is achieved through intelligent data architecture, not simply by increasing the size of the input. Rule 1. Focus on building dynamic systems rather than static text prompts. Rule 2. The quadratic cost of tokens means curation is more valuable than expansion. Rule 3. Spatial position determines performance. Keep your most critical data at the edges of the window. Ultimately, the context window is just a resource. The future of AI development belongs to the architects who can engineer that context.